Alright, welcome back. So in the previous segment we set up our file, set up some layers, made a stock box. Now we're ready to start machining. RhinoCam's machining operations browser is where most of the programming of toolpaths is done. This third section contains all of the various toolpaths that you can make. There's 4 basic kinds of toolpaths. There are 2-axis toolpaths, which are primarily toolpaths in which the X and Y axis are moving, but the Z isn't. So the bit goes to a specific depth and stays there as it moves on the XY. 3-axis operations are when the X, Y, and Z of the machine are all moving simultaneously to carve out complex 3-dimensional areas. 4-axis operations are operations on our CNC router. That's on the side of the CNC lathe that's on the side of the router. And holes, as the name implies, are primarily just for drilling holes. Pretty straightforward. In the case of this model, the first thing we want to do is produce a nice flat face in order for these 2 halves of this mold to mate without plaster or ceramic coming out of that hole. So we want a really flat face. To do that, we're going to use a 2-axis operation. In this case, it's going to be a facing operation. As the name implies, the names are fairly logical. Each of these machining operations is going to present you with a series of tabs, and you have to work your way through these tabs fairly progressively. They're logically arranged from left to right and top to bottom. Once you do that, you can toggle between them haphazardly if you'd like, but you do sort of have to hit all of them or most of them. So the first tab you're faced with is the Machining Features or Regions tab. There are various ways that you can define regions. For Rhino, you can use flat areas, you can use curves, and as you'll see shortly, regions are very important. In this case, we don't have any curves in the model, so we're just going to see what happens if we hit this flat area. That's the face we want to machine, so we'll select that as the machining face. The next tab is the tool, and it's where you select from all of the tools in the tool library. It's a bit easier to see what the tool looks like if you go to Create or Select Tool, where it sorts them by the shape of the bit. Since we're making a flat bottom in this case, we're going to use the flat bottom cutters. The naming convention, or an end mill. The naming convention is what the bit is designed to cut, what the diameter is, whether it's an up or a down flute direction, the number of flutes, and the length of the cutter. The tool number is also indicated over here. Our tool changer has only 10 tools, which is 9 more than it had before. So you want to make sure that that's one of the tools. And then want to get to know which tools we have sort of permanently mounted in there, because if a tool number is tool number 0 in the tool library, you'll have to change the tool before you can cut your file. So in this case, we're going to use a broad end mill since we want a good flat surface and we're not cutting too much material and we know it can handle it. And that is tool number 10. So that's a 3/4 inch diameter end mill. Hit OK. You can see that the tool number again is indicated, and the tool gets highlighted here when it's in the file. So that's useful to refer to later on. Feeds and speeds are loaded by default from the tool. If you ever see very, very small numbers here, you have a funky tool library, or it's downloading the feed rate from RhinoCam instead of from the library, so keep an eye out for that. Generally, you want it to be in the hundreds, not in the single or 2-digit numbers. Spindle speed is something that we tweak to try to get the best possible cut and chip combination. So that's something that, as you come into the shop, that's probably something that will help you adjust. The feed rates also are sort of generally recommended, but not in any way absolute, and these are numbers that we tweak quite frequently, both in the tool library and in the shop when you come to cut your parts. Clearance plane tab establishes the height that the router goes, or the router bit goes above your stock box. In this case, I have the stock box hidden, but you can see the clearance plane is clearly above our workpiece. You can't turn the stock box on right now, but it would be above the stock box as well. It's important that that clearance plane is always well above your part and well above anything else you might have on the router table, like clamps or fixtures or anything like that. Because when the router bit is above that clearance plane, it's what's called rapiding, and if it runs into something, it could break. The roughing pass, in this case, there's many different passes in a lot of different tool paths. They're not all unique. They're not all the same. Roughing is sort of a typical operation for a facing, but we're actually going to use it for a finish. But you always want to double check the stock number and make sure that it is 0 if you're trying to go directly to your model surface. If you want to leave a little bit of extra material for a finishing pass, then you can add that to 1/10 of an inch or whatever you want it to be. In this case, that's going to be our finished height, so we're setting the stock number at 0. Most tool paths have, various ways that you can tell the machine to go, and if you toggle between these, usually there's a little preview that will indicate what it's going to look like. We're going to go with island in this case. Cutting direction is the direction of motion of the router in relation to the direction that the spindle is spinning. Upcutting is generally what you want to do when you can in order to get the best chips and the best results. Step over distance is either a percentage of the bit diameter or a distance, and it's how far the bit moves over between tool paths. In this case, we're going to go 75% since it's an end mill and we're only cutting through 1/4 inch of green plaster. We can do 75% without any problem. That's something that you want to consult with us on. The higher the number is, the faster it's going to cut it. The smaller it is, the better resolution, especially when you get to fall-in bits, which we'll get to shortly. Cut levels is how far the bit is going to move from the top to the bottom. You can assign the location of the cut geometry. In this case, we're going to have that flat area that we selected is the bottom of our cut. We're going to go 1/2 inch deep. We know that the stock box is about 1/4 inch taller than the material, so it's going to start in midair and work its way down into the material. You can do this in one or multiple passes by moving these sliders. In this case, we're going to do the entire 1/2 inch cut in a single pass. And you can assign depth or level first if you're doing multiple depths. Entry and exit is common to many different tool paths. It's how the bit enters the workpiece and exits it. When possible, it's a good idea to use entering along the 3D path because it ramps the cutter into the material rather than slamming the cutter into the material or plunging the cutter into the material. You'll get a better cut, transfer less rotational inertia to your part, and just have generally better results. You want the height of that path to always be at least as high as the depth of your cut. So our cut was 1/2 inch, and our height of this ramp is going to be 0.55 inches. 2D exits are generally not necessary on the CNC router. We do use them on the plasma cutter, and they just add sort of a pigtail at the end of the cut to get the cutter away from the edge of the material. Advanced cut parameters is not generally something you have to tweak, but it's there if you need it. So once you toggle through all those, you can hit the generate button and you get some visual tool paths, which you can toggle on and off to see what they look like. This is a somewhat curious tool path. You can see all of these yellow lines and red lines are the bit going up and over the material and up and over this this void in the center. We actually want to cut away that void in the center, so I have a single flat block. So as a result of having used this flat machining surface, we ended up with this toolpath, which is not exactly what we want. What we can do is make a different region. In this case, I'm just going to draw a rectangle to the extent of that top surface. Now, without editing anything else, I can go back into the toolpath that we just made. I can select the flat area, remove it because it didn't work, and now I can select a new area. And now I can select that square I just drew, which defines the entire, if that were an entire flat surface, it would define the whole thing. Without going in and tweaking anything else, I can just hit the Generate button, and there, with a single click, we had much better results. This is going to be faster. It's going to give us probably a better surface finish, and it's more what we want. Once you get your toolpath you want, you can switch from the Programming tab to the Simulating tab. Once you get to that Simulate tab, you can just push the play button, and RhinoCam will go through a visual representation of the bit cutting out your material without any noise or any dust. It's a miracle. Okay, and then once we get the first facing toolpath down, we're ready to move on to make some three-dimensional toolpaths in order to carve out this void that our ceramic is going to get cast into. So back to the Programming tab. In this case, we're going to go to a 3-axis toolpath. There's a lot of these. Since we're cutting plaster, we can basically move directly to finishing passes. We don't have to do roughing passes as we would have to if we were cutting aluminum or wood or some other denser material. I think we're going to start with a simple parallel finishing path, which is a toolpath that we use quite frequently in the shop. We'll retain that same drive region that we used in the first toolpath just to see what happens. By default, when you move from one toolpath to the next, the previous tools and other parameters will sometimes be copied. For 3-axis carving, you generally would not use a flat end mill, so you go back to selecting tools, and you want to switch to the ball end mills that have a radius end, which are much better for 3-dimensional carving. And again, diameter is going to determine sort of your scalloping effect on the bottom of your mold. So a larger bit will cut faster than a smaller bit. Will take more material out. It's always a balance between speed and resolution. We're going to go with tool number 9, which is a 1/2-inch medium length ball end. Feeds and speeds loaded automatically from the tool. I am going to once again adjust the spindle speed. Clearance plane, again the default, which is right above the stock box, which is good for now. Cut parameters, again we have that stock number, which is how close it's going to get to your model. Since this is a finishing pass, the default number is 0. These in and out tolerances are the approach tolerances and are not all that critical. Cut direction, in this case, since it's going to be moving in a different orientation, we're going to go with a mixed cut direction, which will give us faster results. You can start at the bottom and the top. Our router generally starts at the bottom, so in order to minimize sort of rapid moves to get to the other side, there's no reason to start anywhere else. The angle of your cuts is the angle relative to the router bed. 0 would be along the x-axis, so 90 degrees is going to cut this along the y-axis, which is the direction I want to cut it. And again, the step over distance determines somewhat the resolution of your part and seriously affects the speed that it cuts. So ask to see the sample board in the shop of output at various bit diameters and tool steppers to get a sense of what your finish is going to look like. 25 cents is good to start with. Z containment could be used effectively in something of this depth. Without any Z containment, the bit will go all the way down to the bottom in a single pass. In this case, we can insert multiple step downs, and each time it's going to be 150% of the diameter of the cutter, so it's going to go down 1.5 inches. Maybe we should go 100% of the cutter instead of 150. So it'll go down 1 inch each time that it makes a toolpath, which will shortly be illustrated. The highest Z diameter is, the Z height is currently the very top of the stop material by default, and that's good. If you want to, you could go into your model by clicking that arrow and select, that's where I want it to be the highest height, 3¼ inch. Good. And entry exit again. With 3D finishing passes, generally entry and exit is not critical when milling wood and foam and things that we're likely to put on a router. It would be much more critical if you were milling aluminum or steel or titanium. So then, again, you can hit the generate button and you get a preview of the toolpath. We can see that since we didn't make a new containment zone, the entire top surface that we just spent some time making perfectly flat isn't perfectly flat anymore. It's going to be scalloped. And it's a little bit hard to see the stock on, but if we go to the Simulate tab, we can preview this toolpath. 3D toolpaths take much longer to simulate, and you might want to speed up the speed of the simulation by cranking that speed up and also simulating by move, in which case it just steps much more quickly. You can rotate and change viewports while doing the preview, but you can't zoom, so you might want to spend time. So here we can see the result of that Z containment. We're moving down in multiple steps rather than trying to hog all that out at one time. You can also see many yellow vertical moves or approach moves and red rapid moves or departure moves. That's going to translate into the router spending a lot of time going up and down, which is quite inefficient. So for the next toolpath, we're going to tweak this guy again. Turn off our toolpath, turn off our stock box, turn our part back on. One very easy way to define containment zones or machining regions is to use the Dupe function in Rhino. Of course, when you start typing into Rhino, options that start with that start popping up. Dupe face border is a common function for sort of defining machinable edges. So now we've basically made a curve that is that edge of the hollowed out space. There. I do need to split that in order to break it up from the edge of the face that we duped around the edge of it. We just split, and we're splitting that curve. We'll just use that boundary curve to split it. Alright, so now we have a curve that clearly defines the three-dimensional portion of our part. We can go into parallel finishing, select that as our machining region, regenerate that toolpath. Open loop found. Apparently that curve has to be closed. If you get an error, don't panic. Pretty easy to fix. I always hide what RhinoCam has generated by moving out of your machine setup. and into the stock box. I just need to draw a line from that endpoint to that endpoint. Join those two curves. Back to the parallel finishing, drive region. Now I have a closed curve. Try generating again. No open loops. We have generated a toolpath. We have success. If we go back to the simulate and play, shut off the stock box, show the part. We still have Z levels and we still have a lot of very high Z moves, which is going to consume a lot of time. So this is an instance, somewhat unusual, in which we can change the clearance plane to a skim clearance plane, wherein it's going to move just a little bit above the already removed material rather than moving all the way to the top of the part. We generated this, and now all of those rapid transits are below cutout material instead of being well above the material. You can also go back in. You can go back in and adjust these anytime, which is sort of the beauty of it. It's all fairly parametric by changing cut parameters, the containment, and change that Z containment from 1/2 inch to 1 inch, 200%. Now this can be done in 3 single passes. And I think we're good to move on to another. Alright, so to see what we have from the top, you can go all the way up to your setup, turn on your stock box, turn off your material if you want, zoom into the view that you wanted to get. Hit the play button. Of course, the speed can be adjusted as you go. Sometimes you'll want to turn off the tool paths because the blue lines can sort of obfuscate what you're going to get. And at this point, depending on how close you're trying to get to the true geometry of your part, there is a pretty cool function in RhinoCam called compare, where by hitting this compare button, we can compare the machined out stock box relative to the actual model. You can set this tolerance band to what you want your maximum distance between the model and the part to be. So a 1/16 of an inch. Anything that's more than a 1/16 of an inch is going to be blue, and anything that's negative a 1/16 of an inch is going to be red. Green, if it's all green, it's all good. So hit the apply button. It's going to measure all your parts all over the place. So now, unfortunately, when you do this compare function, you can no longer orbit, but we can get a pretty clear sense of how close we are to our machine part. And this is actually much closer than I would have expected with that big of a step over. So right here, it's more than a 1/16 inch of an inch away from the model, but generally pretty good. So just a cool little added bit and piece. Once you get a first toolpath made, it's actually pretty easy to make additional toolpaths. So I can name these. That one's parallel finishing. Once you get one, you can simply copy it, paste an additional one. So you don't have to throw that away. You can experiment and play with other potential toolpaths. Paste a new one. Now I have a new one that has the exact same parameters as the first one. And if I were to play it, it would play the same thing again. However, I can go into it and adjust the step overs or other parameters and easily compare one to the other. I can also add new toolpaths. So we'll make an additional 3-dimensional toolpath out of this one. spiral machining. And these are all basically going to produce different surface textures depending upon the parameters of the toolpath. Spiral machining might be interesting. As you can see, it selected the previous containment region, so we don't have to reselect that. The tool, it selected the previous ball nose tool. We don't have to reselect that. So basically, as you generate toolpaths, it sort of informs the further generation of toolpath. I can switch this, get back to skim at 50,007 inch. So that's handy. Cut parameters. So this one, since it didn't have much in common with the first toolpath, I'm not sure if these parameters are going to be the same. I want to conventional cut this in order to get better results because the bit and the direction of the cut are going to be moving into one another. Starting point, inside or outside. I think for this, inside seems more logical. Minimum radius, I believe, is how close together the spiral will be. Obviously, the spiral will sort of widen out as it gets out from the center. Let's say the minimum radius is 0.05. Let's see what happens. I can specify the center point. Looks like the default center point is the dead center of my workpiece, which would probably be fine, but I think for the sake of interest, we'll specify a center point either by typing in numbers or by referring back to the model. And let's try to get sort of in the center of this mass. Let's try. All my snaps are off. I wonder. Let's snap to that midpoint. Bam. Maybe about there. So now it calculated where I just snapped to. We'll leave the cutout, the step over the same. Z containment. Can go back to leave the highest Z where it is. Insert multiples again, and we'll go down 1 inch at a time again. And I can generate back to my perspective viewport. Turn on my toolpaths to see what it looks like. So there, we're going to get a slightly different texture result from this machine. Once you have toolpaths, you can easily just rearrange them by dragging and dropping, and they're going to cut in the order that they appear from the top to the bottom. And if you don't want one anymore, you can just delete it. So this one's spiral. And back to the Simulate tab, we can see what this one's going to look like with the end product. You can see that fast preview is just of the facing cutter. It will always preview from the top to the bottom of the top viewport. If I had this machine operations below the other, it would have previewed after the parallel finishing toolpath, and it wouldn't be easy to clearly see what the result of this machining path is going to look like. So there's spiral machining. That's pretty cool. And I think basically at this point you guys have a sense of what it is to program 3-axis toolpaths for these molds, and you can start playing with these other ones and see what the output looks like. Basically the machine is going to produce what this preview looks like. So as long as the preview looks right, you should be ready to machine, and come on down and we'll show you how to use the post processor to create your toolpath. It's always a very good idea to check your front or right side view and make sure that you don't have anything way down below your part or way up above your part. It's a clear indication that something's wrong. If you've got red lines way up here or something, or anything below the spoil board, you got problems and something's going to crash. So we'll catch you guys in the shop. Come down, ask questions, send them to DigiFab Lab, and looking forward to seeing you.